Greetings. In our last exercise, we calculated the lattice energy for the formation of rubidium chloride using the Born-Haber cycle. This time we're going to look at the same problem, and we're going to approach it from the Hess's law type of approach. So let me bring forth the values that we used. Now, what were we trying to do? We're trying to find out the enthalpy, the lattice enthalpy for the formation of rubidium chloride. So the definition of the lattice enthalpy is the energy required to bring the gaseous ions together to form the crystal. Now, realize that many books call the reverse reaction the lattice energy. That is, I have a crystal, how much energy is required to break the ions apart into the gaseous phase, okay? And if it's exothermic in one direction, it's endothermic in another direction, and you don't have to be confused, just look at the sign, okay? It always takes energy to break the crystal apart into its ions, so this direction is the endothermic. Okay, now we have a bunch of thermodynamic values up there in the overlay, and what we want to do is we want to make rubidium chloride, and we know that we can go to a table of enthalpies of formation, of which is one in the back of your textbook, and we could pick that up. Now, the difference between this equation and the enthalpy of formation is that in the enthalpy of formation, we're making rubidium chloride by its elements in their standard state. So rubidium's standard state is a solid, and chlorine's standard state is a gas. Now, this is a molar equation. There's a molar energy associated with it. And so we could have half a mole of Cl2 as a gas, okay? And I'm going to put over here the energies, and these would be in the units of kilojoules per mole, okay? And for rubidium chloride, that value is minus 435.4, okay? And all of these units will be in kilojoules per mole, okay? Now, I have rubidium as a solid. I want it as a gaseous cation, okay? So I could go over and find the enthalpy of sublimation, okay? That is, if I have rubidium as a solid, and I add energy to it, I can make it a gas, and that's the delta H of sublimation, okay? Which from our table up here is 80.9. Now notice that as I go from a solid to the gas, since this is the standard state, the enthalpy of sublimation is the enthalpy of formation, okay? So this value from our table over there is worth 80.9 kilojoules per mole. Okay, now I don't want to make rubidium gas. I want to actually make rubidium solid so that these cancel. I want the gaseous phase to be a reactant. So in essence, we're not subliming the solid, we're doing deposition. We're doing this in the reverse direction. So we want to form rubidium solid energetically from the rubidium gas, okay? So if it was endothermic 80.9 this way, it's exothermic 80.9 this way, so it's a minus 80.9 kilojoules per mole. And now my rubidium solid cancels out. Okay, now I need to convert rubidium a gas to rubidium cation. Okay, so what process was that? Well, in Gen Chem 1, that was our ionization potential. Specifically speaking, the first ionization potential, the energy required to remove one electron from the neutral atom, which was 403 kilojoules. But once again, we're doing this in the reverse. That is, we have the rubidium gas on the right-hand side of the equation, and we have rubidium gas as a cation plus an electron on the left-hand side. So if going this way is 403 kilojoules per mole, going this way is a minus 403 kilojoules per mole. But I'm leaving those out because I have it up here, okay? trying to keep my chalkboard neat. Okay, now my rubidium gas cancels, and I have rubidium gas here, I have rubidium chloride here, and I have 1/2 Cl2 here, but I need Cl minus. Okay, now how do I go from Cl2 to Cl? Well, I have to break a bond. And if we look at chlorine, there's only one bond in it. It's a diatomic. If it was a more complex molecule, we'd have to draw the Lewis dot structure if we're going to use a bond dissociation energy, okay? So the bond dissociation energy for chlorine is 244 kilojoules. That means it takes 244 kilojoules to break this bond and convert Cl2 to 2 Cls, okay? But I don't want 2 Cls, I only want 1, so I'm going to use half that value, okay? Or 200, half of 244. Okay, so let's look at it. I want the Cl2 on this side, so I have Cl2 here, and now I want a Cl, but I don't want 2 Cls, I only want 1, so I have a half of Cl2 here. And these are gases, okay? And so if going this way was 244 divided by 2, going this way is a minus 244 over 2. Remember, we're dividing by 2 because that's the bond dissociation energy for breaking a mole of Cl2, which gives you 2 moles of chlorine. We're only breaking a half a mole, which gives us 1 mole of chlorine. Okay, so now let's see. The half Cl2 goes. And if I added these energies, this would describe the reaction of this plus this plus this to form this. But that's not what we want. And what we notice here is that we can use the electron affinity. Okay, now if you remember from Gen Chem 1, electron affinities can be endothermic or exothermic. Ionization potentials must be endothermic. You must add energy to remove an electron. This can be endothermic or exothermic. And so we look it up, and it's a minus 349 for the electron affinity. Electron affinity is if I take a chlorine and add an electron to it to form chloride. So this direction here, the electron affinity of chlorine to become chloride, is minus 349. We've written it backwards, so it becomes a plus 349. Okay? Now I can go through this, okay, and I notice that my molecular chlorine cancels. And this is a gas phase. And I notice my electron cancels. And so when I add these equations up, I have Rb plus as a gas plus Cl minus as a gas, forming RbCl as a solid. So these equations sum to the equation I want, which then gives me a value of minus 692.3 kilojoules per mole, okay? And realize that this is the same problem that we solved in the previous Born-Harbor cycle. And I'll leave this slide up for a moment, but you can see that these values are the same as up there once I had solved for the cycle. Okay, so I hope this helps, makes everything crystal clear.